You will now be placed into conference.
Anisha, if you have a question in queue.
Yeah.
Okay, you just saw it.
Yeah. 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 So think about your questions in the meantime. Let me see. Okay. So I'm trying to. Okay. Good. Display this note. Okay. Brief overview of OFDM. Brief review. Okay. Sure. And we have one session. I think that was the last one, number 2, session 2. So if you want, you can listen to that. Okay, we have recorded that if you want more details. But let me give you the brief overview. So here is the basic idea. Let's say I have 10 megahertz spectrum. And for LTE, there would be 600 subcarriers, F1, F2, F3, up to 600. Okay. And the spacing between two subcarriers is always fixed, 15 kilohertz. So if I want to construct a subcarrier F1, I would have one full sine wave inside the useful symbol time or modulation symbol period of 1 divided by 15 kilohertz, 66 microseconds.
Nisha, if we can't see what you're drawing, it still says application
sorry, yeah, I got 3 negative acknowledgements. 4, the hybrid ARQ working very, very fast. So you guys believe in hybrid ARQ, not ARQ. Okay, let me try to do some trick. Okay. Okay. Let me change my... Oh, sorry about that. I lost my regular interface, so I need to. Okay, maybe this one. Okay. Okay, give me a few more seconds now. I will try to share the other one. Now we are in business. Okay. Very good. Now you should be able to see.
Yep, looks good.
Okay, very good. So F1, subcarrier F1, we have one full cycle of the sine wave, and within that time period, we are sending one modulation symbol on F1. I want to construct F2, that will have 2 full cycles of the sine wave. Similarly, F3 would have 3 full cycles of the sine wave, again within the same modulation symbol period. So each one basically carries one modulation symbol. And if you construct these subcarriers in this fashion, then you have constructed orthogonal subcarriers. And the beauty of orthogonality is that there is no interference among those subcarriers. Since you do not have to worry about the interference among the subcarriers, you can squeeze in many subcarriers within the available bandwidth. In LTE, we squeezed 600 subcarriers in 10 megahertz bandwidth. And when we want to send data to a user, now we can give all those subcarriers to a user, and parallel transmission on all those subcarriers will give the user very, very high data rate. That is the basic idea behind OFDM. That we give the user several subcarriers and we send data to the user in parallel. So parallel transmission of modulation symbols will give us very, very high data rate. And since we do not have to worry about the interference among those, we can put many subcarriers within the available bandwidth. So hopefully this is what you are looking for. But if you need some additional information, feel free to stay around once the session is over, and you can also listen to a previously recorded session. Okay, any other questions? Follow-up question, clarification, more details? no limit on the number of questions that you can ask. Remove your fear. You always wanted to ask that question. So now is your chance. And you have no more pressure. So release your pressure, ask me that question. Only you know what you want to get out of this session. You want to make sure that you maximize your investment. Okay, you have invested about 4 hours. So please maximize the return on your investment. So go ahead, make this session customized for you. Any questions? And we do appreciate your questions. You have asked good questions using the questions box. But if you prefer audio bridge, go ahead. The window of opportunity is closing very fast. Anyone who is interested in taking my offer, I will give you 30 seconds. 20. 5. I have no timer. I am just making up all these numbers. Okay, let's mute the bridge and take care of the remainder of the...
The conference has been muted.
Okay. So we know all the downlink channels and the signals, how they are used. So we looked at primary signal, secondary signal, broadcast channel, self-specific reference signal, control format indication channel, the downlink control channel, physical hybrid earth indication channel, and then the downlink share channel, the 300 megabits per second pipe. So we looked at all those signals and the channels, and now is the time to take a look at the uplink. That's what we'll do for the next few minutes. Just like we have the reference signal in the downlink, same way we have reference signal in the uplink. It is called demodulation reference signal. Okay, so every UE that is sending out some sort of channel, such as high-speed uplink traffic channel or control channel. Okay? So whenever we send those kinds of channels, along with that, we will send the reference signal. So basically, the E node B has now a little bit simpler task of figuring out what is on those other channels, because we have a very good reference as our baseline. And of course, we have been doing this for a long time. Let's say 2G systems, 3G, and now even LTE, using the concept of this reference signal. So nothing new from that perspective. The reference signal will essentially help the E node B figure out the content of the traffic channel and the control channel in the uplink. And the standard defines specific time slots for the subcarriers that will carry the reference signal. So the physical uplink shared channel. So whatever subcarriers the traffic channel is using, same subcarriers will be used for the reference signal as well. And depending on the certain conditions, we will send the reference signal in a specific OFDM symbol. Okay. So let's say symbol number 3 would carry the reference signal. Other symbols will carry the traffic, but symbol number 3 would carry the reference signal. Okay. The specific pattern that we send on the reference signal is again based on Z of Q. It is better than sending some random sequence because they have good cross-correlation properties. Okay. Now there is a very nice feature. We have so-called sounding reference signals. And the basic idea there is to help the E node B figure out the uplink channel condition. Now we just mentioned that we have this demodulation reference signal, right? That is helping us demodulate the traffic and control channel. Then why do we have this another so-called sounding reference signal? So let's take a simple example. In the past, our base station has allocated maybe, let's say, physical resource blocks, maybe 22, 23, 24, something like that, to this UE for uplink. So our control channel DCI format 0 provided this kind of allocation to this UE. Now our UE will send the data, right? So if I have this 10 megahertz bandwidth out of 50 resource blocks, 0, then 1, 2, out of total of 50 resource blocks, I have given 22, 23, 24. So maybe somewhere around the middle part of the spectrum. Okay, so those are my resource blocks. Okay. So let me use little lighter color so that we are able to see that little better. So here, center part of the spectrum. So that is the basic idea, that we have allocated some bandwidth to the user, and the user is trying to use those resource blocks for uplink transmission, UE to the E node B, 20 to 3 and 4. Now inside that we have shared channel, that is the traffic, and we have demodulation reference signal. So this is the reference. So as this E node B, we can look at the reference signal, and then we know how good or bad the channel conditions are within the allocated bandwidth. So we can easily figure out what is happening inside that part of the spectrum. However, we have no idea about the channel conditions for that user in other parts of the spectrum. That's where the sounding reference signal comes into the picture. So we will have this UE send sounding reference signal. So maybe we will say that this is just one example. This standard is quite flexible, but UE will now send some sort of reference signal. Okay, maybe throughout the bandwidth, if for some small time period, tiny time period, we are sending out sounding reference signal. Our E node B will take a look at the sounding reference signal coming from the UE, and we all these subcarriers, excellent channel conditions in the uplink. And this the other part, maybe let's say okay channel conditions, and some other part poor channel conditions. So as E node B, now we know which part of the spectrum has what kind of channel condition. Since we now know that this part of the spectrum, our UE has pretty good channel conditions, so the next time around we can allocate uplink resources that are from this part of the spectrum, so that we can, let's say, TRPs 0, 1, 2, etc. So now, since we have excellent channel conditions, we can even use high order modulation, 64 pump. We can use very little redundancy out of turbo coding, and then that will basically give us very high data rate. So our throughput will go up. So in summary, the sounding reference signal is giving the E node B a better idea about the prevailing channel conditions in larger part of the spectrum. If you do not have sounding reference signal, then the only thing we know is what is happening in the tiny spectrum bandwidth that has already been allocated to the UE. Okay, so if you want to figure out what is happening elsewhere, then that's where your sounding reference signal will be coming in quite handy. So now we know all about why we have the sounding reference signal. Just another reference signal, but it will help the base station schedulers figure out the resource allocation. Another uplink channel, physical random access channel. Okay, now how do we use that? Well, we have a need to contact the network, but we do not have any dedicated resources. So we have to use some sort of common channel. And just like 2G or 3G system, the common channel here is the random access channel. Where is that channel? Well, 6 consecutive resource blocks. So it will correspond to 6 times 12, 72 subcarriers, about 1 megahertz spectrum. But it doesn't have to be in the central part of the spectrum or wherever. It doesn't have to be. We can put that random access channel anywhere, and the system information will tell you the location of the random access channel. So if we have, let's say, this uplink bandwidth 10 megahertz, then maybe we want to say, okay, this part of the spectrum is your random access channel. So our E node B can specify that kind of information to all the UEs in that cell. So all the UEs know that whenever they want to contact the E node B, they can use that random access channel. So it's a common channel. In terms of time, at what time we can send that, it depends. There are several formats of so-called preamble. So basically, our UE is sending out physical random access channel preamble. And the preamble has several formats. Okay. So it can occupy 1 subframe, it can occupy 2 or up to 3. Depends. And when we send, let's say, one preamble format says that it occupies 1 subframe. So those many resource blocks during 1 subframe. Now the question is, can you send that in subframe number 0 or subframe number 2 or 7? During which subframe can you send the random access channel? So there are some configurations defined by the standard. So one example would be odd subframes are allowed in that cell. Another configuration says only even numbered subframes are allowed for the random access. So there are several configurations, but basically as a UE, you already know those things by observing the system information blocks that appear on the broadcast channel. So no need to worry. You already know at what time you can send that and on which subcarriers you will be able to send the preamble. And the exact sequence as a preamble would occupy 839 bits. We have a question. Is the physical downlink control channel shared among all the users within E node B? Yes, that is correct. And let me just give you an example. Okay, so downlink control channel Yes, shared among all the UEs in a cell. So as a very simple example, the control format indication channel says that only one symbol is consumed by the control channel. Then all these UEs inside the cell know that they just need to process only the first symbol, symbol number 0. Symbol number 1, etc. So let's say 1 millisecond subframe. So we will just look at, let's say, this is one control channel, another control channel, another control channel, another control channel. Okay. So this would convey, let's say, downlink allocation for UE1. This may convey downlink allocation for UE2. This is uplink allocation for UE3. Uplink allocation for UE4, etc. So one control channel carries allocation, could be uplink or downlink for one UE. Another control channel occupies the certain number of resource element groups to convey allocation for another UE. So how does the UE know the resources allocated from the shared? Oh, I see. So I give you an example. So basically, so this downlink allocation, this message, okay, the allocation message is, okay, so we have some allocation message based on which we calculate CRC, and then we scramble the CRC using CRNT. So this UE here is CRNTI X. Another UE has another CRNT like MAC index, voice code, OVSF code, another UE, another ID, and so on. So once you calculate CRC for that message and scramble using the CRC, all these UEs will try to figure out the match. So UE1, let's say this one. Let's pretend that we are UE number 3. So this is control channel 1, PDCCH1, number 2, 3, and 4. Okay. So first we look at control channel 1 and see, do we have CRC match? Now that one is for UE1. Right? It will be scrambled with CRNTI X. And we are UE number 3, so our CRNTI is Z. So X and Z different, so no match. It means that this is not our allocation. Then we go to the control channel number 2. Do we have match with CRC in that case? Now number 2 is for UE number 2, and UE2 has CRNTI Y. But we have number Z, right? That is us, number Z. So why not Z? So again, no match. But we stay optimistic. We say, okay, let me try one more. Keep trying, keep trying. Control channel number 3. Do I have CRC match? Let's try. Okay. Oh, this is our allocation. So it is scrambled with CRNTY. Now we know this is our allocation. So hopefully now you know exactly how the control channel is checked. So it's basically blind detection. So you keep trying all the control channels inside that symbol, and if one of the control channels has your CRC match, then you have allocation. Otherwise, you go to the next subframe and again try the same processing. Okay. But anytime you want more explanation, just send your question. Okay. Looks like you are doing just fine. Thanks for your question. Okay. So where were we? We were discussing the uplink control. Yeah, we looked at sounding referencing. That was our last topic in the random access channel. Okay. So this random access channel, within a cell, we have 64 sequences available. So the UE will randomly pick one of the sequences. And again, we are using this magic Z of 2 sequence. Now, something different from what we have seen so far. The subcarrier spacing is now 1.25 kilohertz only for the random access channel for preamble subcarrier. So what we are saying here is the following. So let's say we allocate out of this 10 megahertz bandwidth, maybe we allocated this 1 megahertz spectrum for, okay, this is uplink, physical random access channel. So 6 resource blocks, and within a resource block, a dozen consecutive subcarriers, 72 traditional subcarriers corresponding to the bandwidth that is about 1 megahertz. So we have reserved 1 megahertz spectrum for our random access channel within some specific subframe. Now, actually, what is inside that is quite interesting. Now we have tiny subcarriers from F1, F2, F3. So we have many subcarriers because the spacing is only 1.25 kilohertz, not 15 kilohertz. Normally we have 15 kilohertz spacing, but for the random access channel is tiny, and on this one we send, let's say, complex number A plus JB based on Z of 2, then F2 C plus J D, some other complex number, etc. So we are using this Z of 2 sequence. Complex numbers are now being sent on that random access channel, but we are sending quite a long sequence. Since the sequence is long, we have many subcarriers. I think about 840, about 840 subcarriers. And the reason that we have so many subcarriers is the spacing is very small. Okay, so that will help us send out a longer sequence, easier for the base station to separate one user from another and to detect the preamble coming from a given UE. More efficient. Okay, any other, okay. And let's say we are a UE and we send this preamble during, let's say, subframe number let's say 8. So we have 10 subframes, 0 through 9, within one 10 millisecond radio frame. So out of those 10 subframes, we are picking subframe number 8. At that time, we are sending preamble. That corresponds to random access radio network temporary ID of 8. So these, whatever subframe number you pick, that becomes your random ID. A little bit later, the base station will send you a response, and it will say, oh, I heard a UE that has used the random access RNTI of 8. And let's say we pick the preamble number 21. We have 64 options. So we randomly pick one of the 64 options. Let's say number 28. And preamble number 21. So this base station is telling all the UEs in that cell that I heard some UE that has used random access RNTI 8, and that has sent me the preamble number 21. And then we are so happy because, oh yes, this is us. We indeed use subframe number 8. So our array RNTI is 8. Not only that, we have a match with our preamble sequence number 21. So then we know that, oh, the base station heard us. Okay, so that's the idea. Okay, very good. So for the uplink, we looked at the reference signal, the random access channel, and now let's look at the uplink control channel. So we have two channels left, uplink control channel, uplink shared channel. So those are the two channels that we will see. Okay. So uplink control channel. What do we send on that? For example, something that is related to the downlink transmission. So CQI, scheduling request for uplink resources, hybrid ARQ, ACNEC. Okay, let me give an example. So let's say our base station is getting CQI, channel quality indicator. Let's say value number 14. So that corresponds to excellent downlink channel condition. Excellent downlink channel. So the base station knows that this UE has super duper channel conditions for the downlink. So let me send lot of bits to the user. Maybe I will use 64 modulation on the high speed downlink channel. Okay, and that will increase my data rate, very, very high data rate. We are able to increase the throughput. So channel quality indicator feedback is very, very important for the downlink transmission. On the other hand, keep some UE far away from the cell side, poor channel conditions, oh, secure value only 2. They say that, okay, I will give you least a bit of data rate, maybe 100 kilobits per second. And I will use QPSK modulation. I will put a lot of redundancy so that the user is able to detect the signal far away from the cell site. So CQI is very, very important. So our control channel is helping us send the channel quality indicator value. Another use of that is scheduling request, right? So let's say this UE, first the buffer is empty, uplink buffer, and after some time, some new data arrives. Packets are arriving now. Now we need to send out these packets, but we do not have any resources. No problem. We will send the scheduling request to the base station. Then the base station knows that this terminal wants to do something in the uplink. then it will allocate uplink resources to that user. So again, to send that in the uplinks, we can rely upon uplink control. That's one way. And finally, hybrid ARQ for the downlink. So basically, the base station has sent us a packet, let's say packet Q. We have had no problem detecting the packet, positive acknowledgement. So no need to do retransmission. So basically, we need a channel to send this kind of ACK-NACK feedback to the node B. And again, we will use the help of the uplink control channel. So in summary, this uplink control channel can send out information such as CQI, scheduling request, hybrid ARQ, ACK-NACK. Now, where is that channel? So there are different formats of the uplink control channel, and I will give you one example. So one possible location is PRB number 0 for the first slot and PRB number 49 for the second slot. That's where the uplink control channel would exist. This is one example, one valid example. Okay. So in this case, it occupies one resource block in each of the time slots. However, we may have multiple resource blocks for the control channel, but this is just one example. Uplink shared channel. This is your big pipe, the 75 megabits per second pipe. Okay. So in the downlink, we support 300 up to 300 megabits per second data rate, physical downlink shared channel. In the uplink, it goes up to 75 megabits per second. So basically, it's nothing but the high-speed channel. And our downlink control channel basically will tell us, right, on which resource block the U is supposed to send the uplink shared channel. What can we send? We can send traffic, we can send signaling messages, we can send CQI, right? This can go over uplink control channel. It can also go over the uplink shared channel. Okay. So it's not necessary that we have to use uplink control channel. We can even use the uplink shared channel to send this kind of information. Let's take a look at some other characteristics of the uplink shared channel. Uplink shared channel, only one antenna will be sending that. Okay. So in the downlink, we have multi-antenna transmission. So the base station can send data to the user using up to 4 antennas. However, in the uplink, only one antenna will be sending out the signal, not multiple. We can do frequency hopping. Okay. So we can send data on resource block 1 in one slot, resource block 20 in second slot, and so on. So frequency hopping is indeed supported. And we have hybrid ARQ supported for the uplink as well. So we have hybrid ARQ in both the directions, just like what we have in 1XE video and HS, DPHS, UPA. Same thing here. Okay. So basically, we have uplink shared channel, right? That is primarily for traffic. But you can also send control information. Okay. You can send signaling messages. Control information here would mean CQI value, hybrid ARQ, ACK-NACK, etc. Okay. So whatever we are sending on uplink control channel, the control information, you can send that also on the uplink shared channel. Okay. Control only. But for the uplink shared channel, you can send traffic, control information, the signaling messages, lot of things. Okay. The last couple of polls. Let's see how well we do here. So we mentioned two channels that can carry the CQI, channel quality indicator. So this should be fresh in your memory. So please do not disappoint me. I need close to 100%. Two channels. We mentioned two channels that can carry the CQI. Which are those two channels? Which were those channels? We just mentioned those. Hopefully your brain is not saturated. Hopefully you have still some room. Which channels can carry our CQI? In one of the sessions in future, we talk about the downlink and uplink traffic. So at that time, we will revisit many of the channels that we discussed today. Okay. But hopefully, I will have maybe 5 minutes or so, hopefully, to summarize these channels. Let's see how well we do. Okay. Maybe 1 more minute. Let me give you 1 more minute. Which two channels carry your CQI? Yeah, I want to give you some review, okay, quick review. So let me move forward. So both the uplink control channel and uplink shared channel, okay, both of them can carry your CQI value. Okay, let me see. Okay, who can send traffic at very, very high rate? Very, very high data rate. Let's see, 1 megabits per second, 75 megabits per second. Which channel? Oh, we have a typo in the first one. Sorry about that. T-Reg only. Random access channel. Random access channel. Okay, there is one channel that will help you send traffic at a very, very high data rate. Which is that channel? Which one? So random access channel, that's a common channel. Anyone can use that in the absence of dedicated resources. Uplink control channel that carries the control information, CQI, scheduling request, ACNAC. So if you want to send those things, do you need 1 megabits per second to send your hybrid RBAC or NAC? Do you think you will need around that? Uplink shared channel, traffic, signaling, control, everything can go on that. Okay, let me move forward. Thank you for your participation. Uplink shared channel. Okay, that's the one that we have for high-speed traffic. What do you think? Is frequency hopping mandatory or it is up to the base station? Frequency hopping for the uplink, right? Who is in control? In OSDMA, there is one entity that is in control. Who is that entity? Who is in charge? What kind of data rate? What kind of modulation? How much coding? How many resource blocks? Who decides all those things? One very, very powerful entity. Is that UE? Is that E node B? Is that MME, serving gateway, PGW? Which one is that entity? Who controls everything related to radio resources? I will give you 30 seconds. But we do appreciate your feedback. Okay. Thank you for participating in all these polls. and thank you for answering my questions. Okay, so it is correct. It is up to the E node B whether it wants to use frequency hopping or it does not want to use. Okay, E node B is always in charge. Okay, what I wanted to do is just spend maybe about 3-4 minutes and summarize all the channels that we have. Okay, how we use those channels. Okay. So basically, once we turn on the power of the UE will look at primary synchronization signal, then secondary synchronization signal, and this will give us cell ID within the group, and secondary will give you the group number. Cell ID in a group and the group number together, we can identify the physical layer cell ID. And these channels, of course, will help us with time and frequency synchronization also. But the byproduct is we know the cell ID. Then we look at the broadcast channel. And the physical broadcast channel will carry master information block that will tell us information such as how much bandwidth are we using. Maybe we are using 10 megahertz bandwidth. Okay. And we look at other channels. For example, once we know the broadcast, we look at the reference signals, right? Because we know that, oh, they are all over the spectrum, cell-specific reference signals. Then we can go ahead, look for control format indication channel that will tell us how many symbols are occupied by the control channel. So let's say this information says just one symbol. Then we can look at the control channel. So it will provide uplink, downlink resources for the user. Okay, it can carry system information, point to system information. So basically, this corresponds to physical downlink shared channel. So the downlink shared channel, if you got the allocation, then you can send traffic, you can send signaling messages, etc. Information about the system comes in system information block, also over the physical downlink shared channel. To support uplink hybrid ARQ, we have hybrid ARQ indication channel that will send ACK or NAC in response to the packet coming from the user equipment. So that is sort of a set of channels that we have in the downlink. As far as the uplink is concerned, we have so-called demodulation reference signal. So basically, it is our baseline channel reference for control and traffic channel. Okay. We have sounding reference signal that will help the E node B figure out channel conditions throughout a larger part of the spectrum. Because the demodulation is only in restricted part of the spectrum. But the sounding reference signal can be as wide as the whole spectrum bandwidth. So we have a better idea about the channel conditions throughout the spectrum. The uplink control channel, that is your control channel, it carries control information such as channel quality indicators for downlink transmission, scheduling request if you have to send some data. Okay. Then you have scheduling request going over that. Hybrid ARQ ACNAC to support hybrid ARQ for the downlink. Then we have the uplink shared channel that is your traffic channel, as big as 75 megabits per second. You can send signaling message, you can send control information such as CQI, TechNet, etc. And in the absence of a dedicated channel, we have the random access channel, common channel that anyone can use to contact the network. So that's what I wanted to convey. Thank you very much for your participation. Thanks for asking questions and answering my questions. So hopefully you learned quite a bit. I will send you the class notes soon. So Dan, you are in charge now.
Okay, great. Thank you, Nishith, and appreciate everybody's participation and asking questions. I have just put up the survey, and you need to go into full screen mode. So you can either use the F5 function key or the expand to full screen mode in your toolbar at the top. But you can complete it just online, and when you have finished, click on Proceed at the end, and that will submit it. If by chance you have difficulty, you can go ahead and close this live meeting and re-enter on that screen, and it should be fine. So if again, I thank you for completing the survey. I share those with Nishith, and he can make mid-session corrections if need be. So I will go ahead and open up the bridge, and if there's any additional questions, you can stay on. But thanks again for your participation.
The conference has been unmuted.
Yeah, okay. Yeah, so I cannot show you the PowerPoint slide or Windows journal notes because you are filling out the survey. It will mess up with your evaluation process. But I will try to give you the information using the audio bridge. So one question that we have is more information on the SIB, System Information Block. So let me give you a couple of examples. One SIB would contain information about how to use the random access channel. For example, when the UE sends a preamble and the network does not respond, then the UE will increase the power of the next preamble. So by how much it should increase power from one attempt to the next? Maybe by 2 dB. So that 2 dB number will be in one of the SIBs. So that's one kind of information. Another kind of information will say, for example, who owns that network? Who is the service provider? So there will be PLMN ID, Public Land Mobile Network ID. So AT&T network will have one identity, Verizon Wireless another identity. So there's another piece of information. Yet another SIB would indicate who is in the neighborhood. So maybe we have other LTE carrier frequencies. Maybe we have GSM, GPRS edge cells. Maybe we have 1X video neighbor, etc. So the information about such neighbors will be there. So one question on full screen mode, F5. The easiest way I think is F5, function key F5. So you can use that to toggle between normal view and full screen. So hopefully that resolves your problem. Okay. Yeah. So those are the main ones. We even have earthquake and tsunami warning system. Can you imagine? We are making so much progress. Right? So if there is some tsunami somewhere, then we'll get a quick indicator about that kind of information. So quite we are responding to the experiences that we have in the past, and we are trying to use the technology to prepare ourselves for a better response. So that kind of. So if you want more than that, what we could do, just send me email Okay, and I will point you to one of the standard specifications. It is basically RRC document, 36.331. Okay, that has all the details about the SIPs. Okay, so hopefully this is sufficient. But any other questions? I'm here as long as you need. Okay, then we have another question. Difference between demodulation reference signal and SRS. Of course. Okay, so let's say I have given a UE. I'm E node B. So I'm in full control of all UEs. So I have given one UE a resource block number 0. Physical resource block 0 for the uplink. So our UE will transmit signals, some traffic or signaling message or whatever, only inside the physical resource block 0. And within that resource block 0, what kind of channels will I have? So as E node B, I will receive uplink shared channel, sometimes uplink control channel from that UE. And along with that, I will get demodulation reference signal. So demodulation reference signal will always exist whenever there is a control channel or a traffic channel allocated to that UE. Since the E node B is observing resource block 0 coming from that UE, it knows about the channel conditions that exist inside resource block 0 for that UE. However, it has no idea about the prevailing channel conditions in all the other resource blocks for that UE. What is happening on resource block number 1, 2, 3, 4, all the way up to 49 for that UE in the uplink? We have no idea as a base station. So if we want to allocate resources to the UE in future, we would like to know how well the channel conditions are for that UE in other parts of the spectrum. So we instruct the UE to send us a sounding reference signal. So the UE will now send a reference signal in other parts of the spectrum, and the E node B can control how much bandwidth the UE can use. So let's say we give the whole bandwidth, let's say. So now the UE is sending the reference signal, the sounding as a reference signal in all over the spectrum. The E node B can now figure out the channel conditions for that UE all over the spectrum, and then it can decide that which part of the spectrum is good to allocate to that UE at that. So in summary, the demodulation reference signal is useful to demodulate the uplink control channel and uplink shared channel. However, only the SRS can give the base station an idea about a larger part of the spectrum bandwidth for that UE. Any other question? And the bridge is unmuted, so feel free to use the audio bridge. So, okay, so looks like you are doing fine. Okay, we appreciate your questions. Any questions? Of course, if you are going away from us, then hopefully we'll see you in a future session, and thanks for the participation. But I'm still here, okay? So keep your questions coming.
And if you have finished the survey and have no more questions, you are feel free to drop the bridge as well as live meeting.
If you do have questions, feel free to stay a little longer. We do not want you to lose your sleep because you did not ask some question. Go ahead. We want you to sleep comfortably, peacefully. So go ahead with your questions.
I know, Nisha, I stay awake at night thinking about LTE.
So Dan, I was teaching UMTS somewhere, okay, at one of our customers.
Okay.
And that customer had previously used GSM system. It's based on TDMA. Okay. And now I'm teaching them UMTS, which is based on CDMA. And
Right.
in CDMA, we have so-called chips, okay, ones and zeros, like
Right.
this, but we call them chips. So I discussed quite a bit about CDMA and about the chips. So the next morning, one student says, "Oh man, I was dreaming all about the chips."
Oh dear.
Oh yeah. So some people can really get very, very serious. So we want you to relax. So just ask your question now, and then you can take it easy.
Well, Nisha, I think we haven't heard questions for a while. It may make sense just to close at this point. And for those still on the bridge, when I do send you the journal notes, you'll see Nisha's email there, and feel free to send him.
Okay, again, thank you very much, folks. Talk to you in a future session.
All right. Thanks.
Okay, have a nice evening. Bye-bye.
And Nisha?
Yes?
I'm going to, there has been a request to save the annotated PowerPoint, so I'm going to put that up on the screen, save it now, okay?
Okay, good.
Very good. Thank you.
Okie dokie.
Bye-bye.
Bye-bye.